Okay, we've talked a little bit about astronomy, a little bit about physics. We're going to talk a little about chemistry, which will take us into next week, and then we'll start a little bit about biology, and I want to talk about the origin of life and design in nature and how living organisms function. At the school where I'm subbing right now, I told the principal, they need a biology teacher short term, and I'm certified in biology. So I told her, okay, but you have to understand, there's 4 things that the biology books usually say that I think are just absolutely wrong. And she said, yeah, but that doesn't come up till the end of the semester, and I should be gone by then anyway. One of them is the idea that the embryo goes through all the stages of evolutionary development before birth. Another one is the idea that you have leftover organs from an earlier stage of evolution called vestigial organs, like the appendix and the tailbone and so forth. Another is the idea that on the early Earth, when life first began, there was no free oxygen, and that's how the chemical reactions were able to proceed. That's known to be false. There have been discoveries of oxygen in all the layers, all the way down to the bottom, to basement rock. And there's another one, which is the idea that there's mountains of fossil evidence supporting evolution. There's no such thing. The fossils, Darwin even admitted, the fossil record was the most grave and serious objection to his theory, and it remains so. In fact, if anything, it's become more and more of an objection. So I told that to the lady, I have a problem with those 4 things, and I'm not willing to teach those. She said, that's not till the end of the semester, and I should be gone by then anyway. It's an interim position. So let's get into chemistry a little bit. Oh, and next week I'll go over the review questions from this chapter that we just went through. So download the text for chapter 5 from either the Legacy Moodle or from creationorevolution.net. Okay, let me give you a semester-long course in 4 hours. It's going to be kind of hard to do. What's everything made out of? Well, since ancient times people wanted to know. Some were just curious, but others had ulterior motives. The alchemists wanted to turn stuff into gold. You take cheap stuff, junk out of the ground, turn it into gold, and you can become rich. Well, many ancient people, could I ask somebody to give me a refill of water, please? Many ancient people followed the word of Aristotle. Back in his day, he was several centuries before Christ. It was kind of like what people say now, God said it, I believe it, that settles it. Well, Aristotle said it, I believe it, that settles it. Aristotle had an incredible amount of influence because he was a teacher of Alexander the Great. And so when this guy sends his army around and they conquer everybody, you better follow what he says. And he just passed on what Aristotle said. Thank you very much. So Aristotle said that everything on Earth is made out of 4 elements: earth, air, fire, and water. Well, what about the things that are not on Earth? Up in space, the stars. They're not made of the same stuff. They're made out of a 5th essence, which is called the quintessence. So you may have heard people use the word quintessential. Most people misuse it. It had to do with whatever makes up the stars. So we now know that Aristotle was just flat out wrong. Previously, I've talked about a theory. In science, a theory is a proposed explanation that's been repeatedly tested and never failed a test. If it fails a test and it's just a minor failure, we're probably going to modify it. Aristotle's idea, it was totally wrong. So we threw that out. Nobody believes that everything's made out of earth, air, fire, and water anymore, except maybe the flat earth people. He also said there's no such thing as atoms, which we're going to get to shortly. And in physics, he made a great many incorrect predictions, and they were all disproved later. So his scientific statements were terrible. His logical statements were great. He invented the logic we still use, syllogisms and transitive logic and all of this kind of stuff. So if you ever go to the store and see a bag and it says, contains no chemicals, If you buy that bag, what are you buying? Nothing. Everything's made out of chemicals. Now, if they say contains no artificial chemicals, well, I don't know about that either, because all natural ingredients. There's nothing supernatural in that bag. It's all natural ingredients. So if you go to the store and you see something that says contains no chemicals, no, that's impossible. It would just be an empty bag. As far as we can tell, everything is made out of chemicals. Everything is made out of atoms. This is another one of those things that we call a theory, atomic theory. A theory is a proposed explanation that's never been falsified, but could be. If you can propose a test and it fails that test, you admit you're wrong. Okay. Atomic theory says everything's made out of atoms. So how could you falsify that? Find something that's not made out of atoms. We never have. So it's a very well-supported theory. I have no idea how many tens of thousands of experiments have been done that confirm, yeah, as far as we can tell, everything is made out of atoms. So there are now 90 elements known to exist in nature. The only two up until atomic number 92 are, I can't remember the names of the two, technetium and one other one. They've been actually detected in stars. We point our telescopes at stars and analyze the light, and we can see what's up there. So in nature on Earth, though, we've discovered 90 elements, and then in laboratories, people have synthesized another 28. What you do is you take some existing atom that has a certain number of protons and neutrons, and you bombard it with more particles, with more protons and neutrons, like helium atoms or just protons, in a particle accelerator, and if you can get it to stick, you may produce another element. Some of these things have only lasted for a few microseconds, but there were enough records of it that we say, okay, yeah, there is an element number 117. But the ones that occur in nature stop at number 92. So despite what Aristotle taught, Aristotle said this, there couldn't be any such thing as an atom, because that would imply, if here's an atom and here's an atom, look, in between them there's empty space. He said, no, there couldn't be any such thing as empty space, because I'm so smart, you got to trust me. So despite what Aristotle taught, everything consists out of atoms that we've been able to see. Of those, the ones that are used in living things, every living thing uses schnapps. So you think, you go to the store, you need your schnapsing list, right? That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon, hydrogen, nitrogen, and oxygen are the bulk of living things. You got an itty bitty bit of phosphorus in the DNA and the RNA, and you got an itty bitty bit of sulfur in some of the amino acids. But without those things, you don't have anything alive. You can have some other compounds, but it is not alive. And then living things use probably several dozen other elements in addition to that. For instance, your bones, they have to have calcium. Not just your bones, though. Another place that you need calcium is in your muscles. In order for your muscles to contract properly, you have to have calcium in them. I saw an episode one time of a TV show called ER, Emergency Room, and in it they had a lab technician brought in because he had spilled some chemicals on himself. And they said, what'd you spill? He said, hydrofluoric acid. They said, how much? He said, about 1 liter. He felt fine. They said, who's your next of kin? Why? You can be dead by tomorrow. Once you get hydrofluoric acid into your bloodstream, it's going to go and it's going to start taking the most active metal it can find, which is calcium, and it can't penetrate the bones, but it goes right through your heart. And your heart has got calcium helping the muscle to contract. So they told the guy, you're going to die. Once it's in your bloodstream, you can't get it out. So you will never, ever, in a basic chemistry lab, fool with hydrofluoric acid. It's deadly stuff. And when you're working in a lab, if you're working with that, you never sit down. And you always wear a lab coat. If you spill it on yourself, you throw that lab coat off, and you're standing up so it doesn't saturate into your pants or whatever. So some of this stuff can be pretty deadly. All right, mammals use calcium, magnesium, manganese, chlorine in your stomach. You have digestive acids, and we even use a little tiny bit of arsenic. Too much of anything will kill you. Too much water will kill you. Besides drowning, you can die of water poisoning. But you have to have even just an itty bitty bit of arsenic. Okay, I want to talk about the two most fundamental principles in all of science. When you take a class in biology, they're normally going to tell you that the overriding principle in all of science is evolution. No, it's not. It's thermodynamics. Biology can only operate within the laws of chemistry. Chemistry can only operate within the laws of physics. The two best demonstrated laws of physics in the whole universe have to do with thermodynamics. Thermo refers to heat, of course, but energy can change back and forth from heat to light to electricity to various other kinds, various other flavors of energy. And so thermodynamics actually refers to any form of energy. The first law of thermodynamics is called the law of conservation of matter and energy. Now, way back when, 150 years ago, there was a guy named Lavoisier, a French guy that, some of those French guys were pretty good. I'm sorry if there's any French people watching this. I love French people. Lavoisier discovered the law of conservation of mass. This had to do with chemical reactions. You don't lose mass when you're finished. You got the same mass you started with. But later it was expanded after Einstein's realization that you can convert matter to energy according to the equation E equals mc squared. The amount of energy is equal to the amount of mass times the speed of light squared. And we've done this in nuclear bombs and in nuclear reactors. Okay, so we've got to take this into account. So it's now expanded. It's the law of conservation of matter and energy. It refers to the quantity of energy. It can be changed back and forth from one form to another, but energy can neither be created nor destroyed by any known process. So you say, where'd energy come from in the first place? Energy and matter. It could either be an unknown physical process, natural process, or it could be an unknown non-natural process. Well, I'm going to go with a non-natural process. I believe God is the creator who made all of this stuff in the first place. So the second law is called the law of entropy. Entropy refers to the quality of energy. It's a measure of the disorganization or randomness or equilibrium of a system. If you have a star compared to the space around it, like our sun and the solar system, there's so much energy concentrated in that star. The space around it contains very little energy. But is more energy flowing into the sun? No, it's flowing out of the sun. We go from greater concentration to lesser concentration. The second law of thermodynamics, the law of entropy, refers to the quality of the energy. It means that energy tends to flow from greater to lesser concentration. That is, things try to move toward equilibrium. If you put a hot and a cold object next to each other, the hot one doesn't get hotter. It loses its heat, it radiates it into the other one, and they tend to reach thermal equilibrium after a while. So there's a great deal of energy in all of the stars. The second law of thermodynamics, which was derived from centuries of observation, says that, energy doesn't come together by itself. It tries to spread out by itself. So we'd have to ask, okay, how did it get in the stars in the first place? We have no natural explanation for it. There's either an unknown natural process following a Big Bang or an unknown non-natural process. As a Christian, I'm going to go with that one. There's a God who is not limited by natural processes, and that's how the energy got into the stars. So even though we really don't have a good definition for energy, it's often described as the ability to do work, to produce change. But in order for work to be accomplished, there has to be a difference in energy level from one place to another. If it's all the same energy level, you can't do any work because you can't transfer any energy. So, for instance, a steam engine would work by converting chemical potential energy in some sort of fuel into heat. That heat boils water, gives the water kinetic energy, moves it around, exerts pressure, makes something spin. So when you're finished, there's less energy concentrated in the fuel and some of the energy radiated out into space. This always happens. Energy just keeps radiating into space. So the chemists don't understand why. I took a class one time out at UNO, chemistry for teachers, and the teacher said absolutely every process that ever occurs increases the entropy of the universe, but we don't know why. Well, I do know why, because I read my Bible. It says in Romans 8:20-22, for the creation was subjected to futility, not willingly, but because of him who subjected it in hope, because the creation itself also will be delivered from the bondage of corruption into the glorious liberty of the children of God. For we know that the whole creation groans and labors with birth pangs together until now. The universe is deteriorating. That's entropy right there. When God made the universe at the beginning, it was very good. And of course, energy had to keep spreading out, because when Adam and Eve were going to eat the fruit, they had to use it. But it wasn't, we don't know exactly what the conditions were, but it wasn't deterioration like it is now. Somehow, I guess it was perfect recycling or something. So the reason that work can be accomplished right now is that the universe, the earth, the stars, they contain large concentrations of energy, so it's not at equilibrium. But gradually, the energy is spreading out through the radiation from the stars, and eventually the universe is going to reach equilibrium. This is called a heat death. So the energy is gradually moving outward because it's out of equilibrium, but when it reaches equilibrium, no change will be possible. Energy is the ability to produce change. No change will be possible. There'll be no such thing as life. Now the evolutionists will say, well, no, you're wrong, because the second law of thermodynamics has to do with a system that's not subject to outside influences. The heat death, the stars are going to burn out. It's a one-way process. And when I was in China visiting Joe and Betsy, I don't know, 15, 16 years ago, something like that, they were teaching English at Xi'an Petroleum University. And the students there spoke English because they needed to be able to interact with people in the rest of the world. So Joe and Betsy asked the university administration, a communist university, atheistic communist university, if their friend from the U.S., a qualified science teacher, yours truly, could give a lecture on the subject of creation and evolution. They said, sure, no problem. Now, I was teaching in a public school in the United States, and I couldn't talk about creation. But in communist China, in an atheist university, sure, go ahead. So I had about an hour and a half to talk to the students, and they've been taught their whole lives that everything's under control, things are going to get better and better, the government's got this, don't worry about it. And so I said, what can I talk about? Well, they're technical people. I talked about thermodynamics, how the universe eventually is going to die a heat death, given enough time. Of course, before then, all of us will be dead anyway. But one of the students were shocked. One of them said, what can we do about it? I said, absolutely nothing. He said, but what will happen to the universe? I said, it'll die. And I said, that is unless whoever started the stars in the first place and put the energy in the stars in the first place fixes it. And the Bible says he will. So it was wonderful to be able to use thermodynamics to plant some seeds in these young people. But then the evolutionists will sometimes say, yeah, but the reason this doesn't apply is because the Earth is not an isolated system. It's not a closed system. Energy can get in, no problem. So entropy can decrease. Well, you can cause a decrease of entropy, decrease of disorganization, increase of organization under certain circumstances in an open system. the first thing you have to do is have some sort of usable energy coming in. Got to be the right kind of energy. So Ashley just had a little baby. Oh, let's give the baby a lot of energy. Let's set up bombs next to her. No, wrong kind of energy. So you have to have some sort of energy that's in a form that will be useful to that system. And then you have to have some kind of a conversion mechanism to put that energy to use. So let's pile steaks and lobsters around the baby. Well, I'm sorry, her digestive system isn't developed enough that she can convert it into a usable form. You have to have not just the right kind of energy, you have to have a conversion mechanism to put it into a useful form. And suppose you have a newborn baby that has no DNA, and you give the kid all the food you want. Are they going to grow? No, the reason that you got bigger, the reason you grew from a single fertilized cell is because you had DNA. You had pre-existing information that would guide the way the energy would be used in order to put together your body structures. I don't care how much energy you give something, if you don't have pre-existing information, it will not develop into something more complex and more organized. No DNA equals no growth. So people are talking about, well, yeah, the Earth is an open system. Yeah, but at the beginning, supposedly billions of years ago, there wouldn't have been any such thing as DNA. So how could anything have used the energy? Besides that, the energy would have been the wrong kind of energy to begin with. Well, this is where sometimes those that believe in evolution are a little confused. They say, no, you know, things can automatically become more organized just by themselves. Look at ice. If you have liquid water, it'll turn into ice. Crystals are much more organized than the liquid water. What they're misunderstanding is that water always has a bent shape. That's the shape of a water molecule, which was calculated and then it was confirmed by X-ray crystallography. So, yep, that's what it looks like. It's like a Mickey Mouse ear molecule. It's always that shape. But normally, the positive end sticking out and the negative end of another water molecule, they're moving too fast so they can't link up. But when you cool them down, oh, we get an attraction between the hydrogen and the oxygen, and it'll form crystals. How much information have we added? None. The information was always there from the very beginning. It's just that we removed enough kinetic energy so that they could slow down and link together. When we removed the kinetic energy, where did it go? It increased the entropy of the universe. So you can have what seems to be a local decrease in entropy, but it's always at a cost. The universe has got to pay for it. Oh, y'all want to memorize this equation? Things can happen only if the Gibbs free energy, they're in a relation between all this. Okay. Okay, so let's take a collection of random letters. Write down a bunch of random letters. That's what we got. Okay, well, let's put them in alphabetical order. I'm trying to illustrate the difference between information and order. Order, yeah, not the same as information. Let's rearrange those same letters, put them in alphabetical order, and this is what we got. Wow, look how orderly. Yeah, but does it convey any information, any meaning? Let's rearrange those exact same letters. Is that any difference from the previous two? Yeah. Yeah, information is much different than just order. So the idea that, you know, there's more energy coming into the earth and so it could make things more orderly. No, not really. It'll actually make things less orderly, the energy that's coming in, and it's not going to add any information whatsoever. Okay, so back to the idea of an open system. There has to be pre-existing information. Well, yeah, there is in the physical structure of the water molecule. That's why it forms crystals. But then as entropy decreases in my little local area here, things become organized, more organized. It's because the universe is paying for it. There has to be at least a greater increase in entropy elsewhere. There's always a cost. So the idea that if you put in enough energy, you can increase the organization of something is just totally false.
So if there was a big bang, it would have been the most disorganized explosion of all time. And for things to become more organized, it's going to have to become more disorganized than being already at its maximum disorganization. It doesn't work. Okay, so somebody was saying about things changing into different compounds and so forth. So ancient people were interested in turning cheap stuff into expensive stuff. The alchemists, so they're trying to turn just dirt and things like that into gold. So there's a distinction between element, compounds, and mixtures. Elements are things we find on the periodic table. There are 90 of them known to occur in nature. And this is really nice. You can get that on Wikimedia Commons. Just go in there and search the periodic table. There are several of them. This is a basic one, but I'm going to show you later a much more detailed one that gives you some of the very useful measures. Okay, there are presently 90 elements known to occur in nature, and an additional 28 that have been manufactured in the laboratory. So what you do is you take a pre-existing element and you put it in something called a particle accelerator, and you smash it together. Let me get this out. There we go. Smash it together. So we take, say, uranium with it 92, how many protons it has, and we smash a helium nucleus into it at extremely high energy, and if you hit it energetically enough, you can have the other thing kick on. So now instead of 92 protons, you have 94 protons. So you can do it again and again and again. The highest we've been able to get is up to atomic number 118. I think that's as far as we're ever going to be able to go. Because a little later we're going to talk about electron energy level. There seem to be 7 shells of energy level, and by the time you get over here, they're full. And there does not seem to be an 8th shell that you should attach to an atom. We're going to get back to the shells a little bit later. So a compound, as compared to an element, is not found on the periodic table. These are individual elements, scandium, titanium, vanadium, chromium, and so forth. Individual elements, each atom is identified by a certain number of protons. So it's atomic number that you see it says 21, that's how many protons scandium has. 21. Boron, 107. Oh, okay. Bohr is one of my heroes. Milk Bohr. Last week, I think I showed you guys a quote from him, or maybe it'll be back up this week. He was a Danish guy, and he said, if you think you understand quantum mechanics, you don't. Everything that we call real is made of things that cannot be called real. This is the same thing Hebrews 11:3 is saying. The things that do appear are made of things that do not appear. So, from element, the way we tell the difference between an element, a compound, and a mixture is you try to break it apart. You cannot separate an element into anything simpler short of putting it through a nuclear process. An atomic bomb, okay, yeah, you're going to have the uranium split into barium and krypton, perhaps, or something like that. But short of a nuclear process, you can't change the number of protons in its nucleus. A compound is a little different. It consists of 2 or more elements combined in a fixed ratio. If it's not a fixed ratio, like you just say, okay, put some iron, put some carbon in there, that's not a compound. It's maybe something called an alloy. You've probably heard of that, like bronze is an alloy of copper and tin. How much copper, how much tin? Varying amount. And an experienced metal worker will know, okay, if I put a little more tin, it's going to be a little harder. If I put a little more copper, it's going to have a better sound for bell, something like that. But there's not a specific formula for bronze. Whereas there is a specific formula for water, carbon dioxide, carbon monoxide, methane, ethane, ammonia, things like that. So you can separate a compound into simpler components by chemical means. Chemical means would be things like putting in an acid or applying electricity. Why is electricity chemical? Because everything's held together by electrons. So when you apply electricity, you're doing a chemical change or something, and you can break it apart. That's how we get aluminum out of the ground. It used to be that aluminum was extremely rare and extremely valuable, and sometimes tin would give out a thin block of aluminum. But then, when we discovered how to produce electricity at high currents, it's pretty easy to get aluminum out of the oil ore in the ground, bauxite. It's a chemical process. Bauxite ore has got aluminum and other stuff. You apply the electricity, there comes the aluminum. So if the formula changes, it becomes a different compound or element. So for instance, with hydrogen and water, H2O, how can you break those apart? Simple, electricity. You apply a little bit of electricity to it, of direct current, and you can separate the hydrogen and oxygen. And you collect them, and it's really cool if you, on the negative terminal, you're going to get the hydrogen, and the positive terminal, you're going to get the oxygen. You collect those gases, then you allow them to mix together, and you put a little spark in it, and you're going to get the most satisfying bang! You see the one here. Oh, they explode very, very rapidly. You heard of the Hindenburg balloon? It didn't really blow up. It burned. And actually what started that fire seemed to be a lightning strike against the aluminum tin, and the aluminum was what caught fire. Just the hydrogen inside of it had reacted with oxygen, it wouldn't have burned gradually. It would have gone kablooey all at once. Okay, so you can separate a compound by chemical means such as acids or electricity, but then are you an element? Are you a compound? You're a mixture. Everything else is a mixture. It's a collection of elements and compounds that doesn't have a definite formula. For instance, salt water. What's the formula for salt water? Some salt, some water. What's the formula for coffee? Put some coffee in it. There's no definite formula. It's not like coffee 38204. So everything else is going to be a mixture. And mixture or a compound has properties that are different from the elements that make it up, almost always different. For instance, if I take nitrogen, which is a clear gas, lighter than air, much lighter than air, and I mix it with oxygen, and I give it a little spark and it goes kablooey and comes together. Whoa, now it's a liquid. Now it's much heavier than air. The properties of the compound are much different than the properties of the elements that put it together. And another example, table chalk. If you sprinkle on your French fry, sodium, the formula is NaCl. Sodium is an explosive soft metal. Throw it in water, it goes bam! But yet, you put it on your French fries once it's combined with chlorine, and chlorine is a deadly, poisonous green gas. Whenever there's a train derailment, and they had a tank truck full of chlorine, everybody gets so worried. So you put it together with sodium, that's salt, and you eat that. So the properties are very much different when it's in a compound than when it is separate. So you can separate a compound by chemical means, such as electricity, acids, and things like that. Most things are mixtures. You don't have a definite formula, you're a mixture. Your blood is a mixture. It has red blood cells, white blood cells, all of the different things in there. Your cells are a mixture. You can have two different kinds of mixtures. One is called homogeneous, that is the same throughout. You've heard of homogenized milk, right? Okay. When milk comes out of a cow, it's all lumpy. Anybody ever seen milk right out of a cow? No. It's lumpy. It's that clump of fat. So it homogenizes. You put it in like a big blender and chop it up. So they also pasteurize it. Anybody know what pasteurizing is? You heat it up enough to kill the bacteria. So what's the fastest thing on it? Milk. It's pasteurized before you even see it. People that are watching this video think, Okay, so a homogeneous mixture is obtained throughout, even under a light microscope. Now, if you put something under an electron microscope, magnifying hundreds of thousands of times, you can see a difference. But a homogeneous mixture, like sugar water, you can't see the individual molecules of sugar in there, even under a good quality light microscope. Electron microscopes give you clear. So that's generally the standard to be able to tell the difference. And another way you can do that, if you have a homogeneous mixture, you shine a laser through it. Okay? If you can see the beam of the laser in the liquid, then it's heterogeneous. A homogeneous mixture, the light goes right through and you can't even see it. Maybe we'll do that later on. So, a heterogeneous mixture, hetero means other. So, for instance, concrete, there's certainly visible differences in it. You got little rocks and chunks of it's not, and you got garden soil, you got mud and little worms up and stuff like that. Well, that's a heterogeneous mixture. So you can separate a mixture by physical means. You may be able to reach in there with tweezers and grab stuff, or you may be able to shift it or foil it. If you want to get all of the trash out of water, what you do is you chill it, and what you're doing is boiling off the water at a certain temperature at which it vaporizes, and the water goes away, and what's left behind is all the soil. So we have a water distiller we use at home, and it's really disgusting. It's what's in the bottom of that thing every time you distill water. So that's boiling. And you also could use magnets. You could put something in a centrifuge. It's a spinning thing, and stuff that's denser is going to be thrown to the outside. Stuff that's less dense comes to the inside. So actually, when you're trying to make an atomic bomb, you're trying to make an atomic bomb. Oh, okay. So you're trying to make an atomic bomb with two isotopes of uranium in the ground. Uranium-238 and uranium-235. 238 is used for bombs and nuclear power plants and so forth. 235 is the stuff you need. So what you have to do, one of the ways to separate it, is put it in a centrifuge, you vaporize. So we got uranium vapor. Starts with thin. So 238 is slightly denser, it's going to be thrown to the outside. The 235 is going to collect more toward the inside. And when you gradually cool it and it's solidified, the stuff on the outside is the useful stuff. The 238, the stuff on the inside is the useful stuff, the 235. So you can separate not only mixtures of different elements, even mixtures of a single element. That's one of the techniques which you can do. And then, have you ever wondered how you get liquid nitrogen and liquid oxygen and all of that? So, you get so someplace and buy it, right? But how do they separate it? The air is about 78% nitrogen, 21% oxygen, and 1% other stuff. So you take your air and you put it in your machine with very sophisticated equipment, and you start to cool it down, cool it down, cool it down. And when you get to a certain temperature, all of a sudden you get this white solid stuff that we call dry ice. The carbon dioxide which goes immediately to a solid. Okay, you pull all of that out. Now you've got fill a mixture. You pull it more, pull it more, pull it more, and eventually you see one of them turn into a liquid. I don't know which one, liquefied for oxygen and nitrogen. So you get all of that out, and then what's in there, you can just take it as it is or continue to cool it. You get liquid nitrogen, and then the other stuff is in there, and you can get liquid helium and all of the things that are in the atmosphere eventually. It's called fractional distillation. Okay, is this exactly what an atom is like? No. Remember, if you talk about a law of nature, you're saying this is what always happens, you've never seen an exception. If you talk about a scientific theory, this is your explanation for why something happened, and you've tested it over and over again, and you've never seen an exception. So, for instance, we talk about cell theory in biology. That theory is a proposed explanation for why living things behave the way they do, and it says, for one thing, that every living thing is composed of cells, So another thing, the cells only come from previously existing cells, and I don't remember what the other part was. What would it take to disprove cell theory? Find any living thing that's not made out of cells. So it's been tested ever since Leeuwenhoek first observed the first cell back hundreds of years ago, and nobody's ever seen anything that's not composed of cells. So it's a good theory. Never failed to test. So it also enables you to make predictions about what you're going to find in the future. So can we do that with atoms? You can see cells under a microscope. Can you see the details of an atom under a microscope? Even under the best microscopes we have, scanning tunneling microscope, you can see the blurred outline of an atom, but you can't see the details. So it's just too small. So since you can't actually see it, what we do is put together the knowledge that's available to it into something that's called a model. So this is very commonly used, a planetary model of the atom. Nobody believes this is exactly right. It just helps you to get a picture of what's real. So in the center of the atom, we have a nucleus, which is composed of protons and neutrons. And then somewhere moving around are electrons. We used to say they were in orbits, now we say they're in orbital. We'll get to that a little later. So the number of protons determines the atomic number, and that determines what element it is. So the protons attract a specific number of electrons. The number of neutrons keep the protons from flying apart. The electrons are about 1/1836 the mass of a proton. They're about 1/1837 the mass of a neutron. So a neutron is heavier than a proton by about the mass of a neutron. Okay, so when we put together the number of protons plus the number of neutrons, that's called the mass number or the isotope number. I mentioned it a few minutes ago, uranium-235, uranium-238. So uranium has 92 protons. So subtract that from 235, that tells you the number of neutrons in the less stable isotope. Subtract it from 238, that tells you the number of neutrons in the more stable isotope. Okay, as compared to atom, we don't have a complete picture of the atom, but we think we have a pretty good idea. Remember, I showed you guys about the blind men of Hindustan. They encountered an elephant in the jungle, and one of them bumped into the leg and said, "Oh, an elephant's like a tree." Another one encountered the tail to it's like a rope. That's what we have to do with atoms, because we can't see them. They're too small. Well, with molecules, sometimes we can see them because they can be composed of thousands of atoms. But a molecule is a complete self-contained unit and it has a definite boundary. So there's a water molecule. So you have an oxygen atom at the center and two hydrogen, an oxygen ion and two hydrogen ion stuff on there like Mickey Mouse is. That's it. That is a water molecule. So most molecules are the smallest particles of a compound that have all the properties of that compound. So if you apply electricity and you separate the molecule into a component, it's not the same component. So for instance, water, H2O, you separate it, now we've got hydrogen and we've got oxygen and we don't have water anymore. The properties of those gases are completely different from water. Okay, so in general, a molecule is the smallest particle of a compound. However, there's a weird thing, 7 elements on the periodic table that are either gases at room temperature or immediately turn into gases. They can't exist as a single atom. We don't know why, but they don't. So they're off at the upper right corner of the periodic table. It's like a rotated letter L. The hydrogen is up over there by itself. It's one of those that doesn't exist. It's just a single atom. Hydrogen is in the form of H2. Likewise, over on the right side of the periodic table, nitrogen, oxygen, fluorine, bromine, and iodine, those are the other 6. We don't understand why they don't like seeing individual atoms, but they don't. So they're called diatomic molecules. So those also are represented. They're the simplest naturally occurring forms of that element. So H2, N2, CO2, O2, F2, and so now when they're in a compound though, they don't have to be two. For instance, in H2O, we only have one O. Separate it, and you're going to get some H2 and some O2. Okay, and then I'm going to muddy things up even more. There are a lot of things that are not molecular. They're called formula units. For instance, here in South Louisiana, we have a salt dome. The formula for salt is NaCl. Does that mean that's it? It's one Na and one Cl? No, it goes on and on and on and on and on and on and on. So it could form a crystal that could go on just as far as you want. There's some of these that are like thousands of meters long and wide and high. So what we do in order to make it easier to figure out how to put them together, we just say what's the lowest whole number ratio. For every Cl, there's one Na. So we write NaCl. It's not a complete molecule. It's part of a crystal. So a formula unit has to do with crystals that are made of negative and positive ions. Okay, and then here's another thing. In chemistry, we use the word substance differently than we do in ordinary conversation. Regular conversation, when you say substance, you just mean salt, right? Well, in chemistry, when you mean salt, you say material. But if you're talking about a substance has a definite formula. There are two types of things that have definite formulas. One is element. You get their formula right off the periodic table. The other is compound. They have a very specific formula. Carbon dioxide is CO2. Sulfuric acid is H2SO4. Definite formula for a compound. So it can be an element or it can be a compound, but it's got to have a definite formula in order to be considered a substance. Otherwise, it's a mixture. Okay? Moving along to chemistry. So getting there fast. Everything has certain physical properties and certain chemical properties. Physical properties would be things like color, size, shape, hardness, weight, pick it up in your hand. All you have to do to determine the physical properties is just observe the material. Chemical properties have to do with how a material reacts or doesn't react. So what are the chemical properties of this? I'm going to have to try to get into some chemical reactions to see. So one example would be, if I try to react helium with anything, it ain't going to react. That's a chemical property. If it will react, that's a chemical property. If it won't react, that's also a chemical property. In order to detect chemical properties, you have to try to change the chemical formula. You may not succeed. If you don't succeed, you just detected a chemical property. Okay, and then physical and chemical changes. Very similar to physical and chemical property. Physical changes don't affect the formula. For instance, if I take liquid water, and I freeze it, okay, it's still H2O. If I boil it, it's still H2O. The formula is H2O for all of its own. Formula for form, okay. So that's a physical change. A chemical change does require a change in the formula. For instance, if I break water down into hydrogen and oxygen, I start out with H2O, and I end up with H2 and O2. Well, that's a change of chemical formula, so that's a chemical change. And moving right along, what are the states of matter? Well, in the universe, it's not what we normally think on Earth. I've seen videos where they say the states of matter are solid, liquid, and gas. So those are the ones that are most familiar to it. Well, we're made of a lot of solid, a lot of liquid, and some of us have a lot of gas. But you didn't really say that, did you? A solid is something where the particles are moving slow enough to link up with each other, and there's a definite volume and a definite shape. In a liquid, the particles are able to move a bit faster so they can kind of slide past each other. So there's still enough attraction that they don't go shooting off into the air. Liquids have a definite volume and they take the shape of their container. In a gas, the particles are moving fast enough that they break their attraction to each other, and they can go flying away. So a gas is going to occupy the volume of whatever container it's in if it's a closed container. If it's an open container, it's just going to mix in with the gases in the atmosphere. Okay, those are the three familiar ones, solid, liquid, gas. But then, the most common state of matter in the universe, most people don't think about this, it's called a plasma. This is where you've applied enough energy to atoms to remove some or all of the electrons. So it's a bunch of nuclei zipping around, maybe with some of the electrons attached, but they behave a lot like a super, super, super hot gas. If you've heard of a plasma chain redo, you apply enough electrical energy to move the electron off of the atom, and it turns it into a plasma. And it's a work. That's it. This is one shot on video. You're on video. You can't see it, but this is called a plasma globe. There's a little transformer inside there, and there are wavy little filament of plasma. This is about a 900 volt power supply on the inside. It's extremely low current. That's why it's not getting here. It's a very high voltage. And so the gas inside there, I believe it's probably argon. It's very frequently used. So, you see this? Uranium. Yeah, there's a little bit in its it's plasma going around. And it follows the hand. And I used to love to drive people nuts at it. I have a high frequency hearing loss. So I can't hear it, but if you put a coin up top of it, if you finger on, some of you'll hear high frequency. Yes, you don't hear it. Okay, well, never mind. So I used to love to drive my too crazy at that. Said, I couldn't hear it. So this is a plasma. It's what happens when you apply a very high electric potential or ultraviolet gamma ray or something like that, and you strip away some or all of the electrons, it turns into a plasma. The reason I say that's the most common state of matter in the universe is that's what started in. They're so hot that it's just a whole bunch of stuff just going around like crazy. And then there's three more. Back in the 1920s, there was a physicist in India, a guy named Bose, who predicted, so this is about the time that we had discovered quantum mechanics, that everything has a wavelength. So he predicted, if we could get something close enough to absolute zero, like a gas or something like that, the particle nature would disappear, and it would manifest itself as wave. So this was an interesting idea to Einstein. He said, hey, put my name on that too. So they predicted a Bose-Einstein condensate. Nobody ever actually was able to make one until about 1990. 1995. When I went to the American Association of Physics Teachers meeting in Salt Lake right before Hurricane Katrina, we had 3 Nobel Prize winners teaching this. One of whom was the guy that had made the first Bose-Einstein condensate. So you have to get something very close to absolute zero. That means it has to pretty much stop moving. Well, are you moving? Compared to what? Compared to the laboratory where they were doing the work, they had to get it to stop moving. So they fixed up an array of thousands of lasers, and they sprayed some vapor in there. I don't know if it's iron vapor, but some kind of vapor, and they turned on the laser. If one laser hits one atom, it's going to knock it that way. Then if another laser hits it, then it's going to knock it back. And another one hits it, and the atom is floating around. Vaporized atoms are going to go. And eventually, they can't go anywhere because the lasers are holding them in place. And lo and behold, they got a Bose-Einstein condensate. So it was theorized, and it came to be. It's not something you or I are very likely to do, because it requires something close to absolute zero. But yeah, it was a successful prediction of, I don't know what you call the theory. Some kind of chemical theory. And then there's yet another state of matter. It's called a quark group. What's the simplest particles of matter? For practical purposes, protons, neutrons, and electrons. However, scientists have put these things into particle accelerators and smash them together at close to the speed of light, and they break down into smaller particles called quarks. So far, they've discovered 6 varieties or 6 flavors of quark, and they're of no practical use. But still, protons, neutrons, and electrons are made of smaller particles, and it's all made out of waves anyway. It's also called a quark-gluon plasma. This would exert energy so high that the protons and neutrons break down into simpler components that are called quarks. It's believed to have been formed several times in super colliders, like the CERN, CERN over in Europe, I think in Switzerland. Well, it's not anything practical, but it's just somebody said, I want to know. Why did you find that mountain? Because it was there. Why did you want to find out that? Because it was there. Okay, so they've only persisted for a fraction of a second. And that's the basic stuff about chemistry. Now let's get to the periodic table. This is a wonderful periodic table if you can get on Wikimedia Commons. And I don't know who TT is, but when you put it on Wikimedia Commons, you're giving people permission to reproduce it. That's no charge. So whoever you are, thank you very much. This is a great periodic table. It shows the atomic weight or atomic mass. In physics, we make a distinction between weight and mass. In chemistry, we call it all the same thing. It shows the atomic number. It shows a measure called electronegativity that lets you predict how these things are going to get into a chemical reaction. It shows chemical symbol, the name of it. It shows the electron configuration. This is a great periodic table. So anyway, if anybody's interested in chemistry, just go down there. It's on the material that I've uploaded to creationrevolution.net. It's also on the Legacy Ministry College Moodle. Okay, so this lets you make a whole lot of predictions. The periodic table is divided into regions. Most of the elements are metal. Up until the clear cap, everything to the left of that is a metal. The ones along the clear cap, those are called metalloids. They have some characteristics of metal, some of non-metal. And the ones on the right side are called non-metal. Some characteristics of metals is that they tend to be good conductors of heat and electricity, whereas non-metals tend to be poor conductors of heat and electricity. Metalloids, they're controllable. So when you want to use some kind of an electronic circuit, you're probably going to have silicon or germanium in it. We can control the flow of electricity through those by applying bias voltages to them. So they're really, really useful in electronic circuitry. There's a measure on there called electronegativity, and that shows the relative strength of this element in attracting electrons in a chemical reaction. The same guy that got a Nobel Prize for discovering the health benefits of vitamin C, Linus Pauling, I believe he's the one that put together the electronegativity chart. So he ranks the elements on a scale of 0 to 4. So how strongly do they attract electrons? The ones on the left side in group 1 and 2, they have a very low electronegativity, considerably less than 1. The one that's the lowest, I believe, is francium. This just doesn't hold its electron at all. If I'm an atom, I want to have 8 valence electrons. We're going to get back to valence electrons later. Most atoms want to have 8 electrons around the outer edge. So let's say, I have 7. I want 1 more. If I get 1 more, it's going to be slightly larger. It'll be even bigger. So it's easier for me to get a complete set of 8 electrons by taking one. But if there's another atom, it's got an inner set of electrons plus 1 electron on the outside, it's easier for us to have a complete outer shell by giving away one. So those have a low electronegativity, and the one on the left side have a high electronegativity. Elements on the left side tend to lose electrons in a chemical reaction with those on the right side. Those on the right tend to take electrons. But if you have two elements on the right side, neither one can overpower the other one, so they share the electron. They pull pretty equally. So like if there's some food that Jackie and I are fighting over and of equal strength, neither of us can take it away from the other one, so we have to share the food. So they share electrons. They really would like to take them, but they can't. There's no electronegativity shown to the noble gases because they don't get in chemical reaction. Somebody was able to force one of them into a chemical reaction at one time. I don't remember which one. But generally, they don't react, so you don't see electronegativity for those. Okay, there have been many discoveries. I got to fix it straight 75. It's Maffer, it's so smaller. There have been discoveries of even smaller parts, such as quarks, that the ones that we're interested in are proton, neutron, and electron. The electrons are the things that allow everything to combine. But the function of the subatomic particle, in the center of the atom, we have a nucleus. And the nucleus is composed of protons. Okay, I skipped over that. The element symbol is one or two letters, which sometimes doesn't sound anything like that element at all. For instance, lead is 2D, sodium is Na. So these have been known since ancient times. We use sodium is natrium, lead with boom. I don't remember what he was, with some sort of a group thing. And then at the very bottom, there are two rows going across, starting with cerium to lutetium and thorium to lawrencium. Those actually belong right in there. So this is part of period 6. This is part of period 7. The reason they write it that way is so it'll fit on people. Pretty exciting. Okay, so before an atom gets into a chemical reaction, it has the same number of protons which are positive and electrons which are negative, so it's electrically neutral. But when it gets into a chemical reaction, it's happy being electrically neutral, but it would be even happier if it could have 8 electrons in its outer shell. That would mean if it needs to take one, I'll say it's going to be imbalanced. It's going to have more electrons, a little more negative. If it gives up one, I'll say as long as it's empty, then it's going to be a positive charge. So the way you predict how an element will react with another one, you will find the electronegativity chart. If there's a very large difference between them, they go from 0 to 4. The highest one is fluorine, which is a 4 electronegativity. So if you put anything on the left side of the periodic table, sodium, lithium, something like that, with fluorine, it's going to react with fluidly. Or if you put solid sodium with gassy fluorine, it's going to react violently. So if you want to be able to predict whether it's going to be a violent reaction, it's a mild reaction, you look on the chart of electronegativity. So Linus Pauling, the guy that did the vitamin C, he's the one that put together the chart of electronegativity. Thanks to Dr. Pauling. Okay, the classical function. The number of protons, you saw the atomic number, and what protons do in an atom is they pull an electron. That's their main function. See, electrons do everything. So the protons will attract a specific number of electrons. And the protons want to fly apart. If I put 2 positive things together, what do they want to do? Separate. You don't understand why. For some reason, the protons in all of the atoms don't fly apart. Every element in the universe, except for hydrogen, has 2 or more protons. So we have 2 clusters together. They want to fly apart. Why don't they? We don't know. If there's something that holds them together, so let's just slap a name on it. Let's call it the strong nuclear force. Scientists have no idea what it is. It's nevertheless, we call it the strong nuclear force. What is it? We don't know scientifically, but I think the Bible tells us. Colossians 1:17. He is before all things, and in him all things hold together. King James says all things consist, so it means hold together. Why don't all of the atoms in the universe fly apart? See, we have no idea who God is. And Jesus, the Son of God, he is the creator, he's the sustainer. How can a man be born in a little manger in Bethlehem and yet he's the one that holds every atom in the universe together? I don't understand. Do you understand what it's saying? Okay, so the total number of protons and neutrons. The neutrons are somehow involved in the strong nuclear force. If there are too many neutrons or too few neutrons, it's going to fly apart anyway, and the strong nuclear force doesn't do much good. Then when we add up all of the protons and neutrons, the electrons don't count it. So like, add up all the protons and neutrons, we call that the mass number. And there's a scale of atomic mass. So hydrogen is the lightest that has an atomic mass of about 1 AMU atomic mass unit. Helium is 4, and all of the other things have varying amounts of atomic mass. So if I've got uranium 235 has its mass, uranium 238 has a different mass. So what we do is we just average them all up. So if you have 5 different form isotopes, and we say, okay, these are 10%, these are 15%, these are 27%, you do what's called a weighted average to get the mass that's shown on the periodic table. So not all oxygen atoms are exactly 16 atomic mass units. If you look on there, you see 15.99 something. It's even a few of them are very slightly less mass than 15. And electrons do everything else. The universe is held together, compounds are held together, you're held together by electrons. So the proton attracts the electron, neutrons keep photons from flying apart, and the electron puts everything else together. So you can use the periodic table to predict how things are going to react. Niels Bohr was the first guy, he's one of my heroes, he's the first guy that figured out when you're trying to figure out the arrangement of electrons around an atom, he determined that there are 7 principal energy levels, and these things are arranged in what you would call shells. I had another one of these, I don't know what happened to it, but is an electron a wave or a particle? The answer is yes. It's a wave or it's a particle. So this represents an electron moving around the nucleus of an atom. Where exactly is it? I don't know. It's a wave. But then I can have, let's say that represents the whole shell of electrons. Okay. I can also have, I consider it in here. I can also have a second shell, third shell, fourth shell, fifth shell, sixth shell. So here's my inner shell, and I've got another shell. I should have 7 of these shells. That represents 7 principal energy levels possible for an atom. So I've got some inner electron, and then I've got the outer electron. She said a nuclear reaction. I've got the outer electron, which is called the valence electron. These are the ones that do the chemical reaction. The inner electrons are not involved in this. They're just there to hold everything in place. If anybody understands exactly how it works, then you need to report it to the Nobel Prize Committee to get the Nobel Prize. So it works something like that. So the electrons are arranged in shells. You have the closest shell, and then that would be number 1, and then 2, 3, 4, 5, 6, 7. They match up with the periodic table. There's 7 rows going across. Those are called the periods on the periodic table. So when you add up the electrons in the innermost shell, there can only be 2. That's hydrogen and helium. So when you get to the next shell, there can be 8 electrons in that. So the next shell there can be 8. The next shell there can be 18. Next shell 18. Next shell 32. Next shell 32, and that's it. That takes us up to 118, which is atomic number 118. So why is it that the numbers are 2, 8, 8, 18, 18, 32, 36? I'm hoping somebody can tell me because I'll steal your idea, send it to the Nobel Prize Committee. So chemists call those the magic numbers. Why those numbers? Nobody knows. But anyway, those are the numbers. So a periodic table showing electronegativity is also going to hint at something about why the electrons do what they do. The electrons most involved are the valence electrons. So except for the first 5 elements, they don't have enough protons to track 8 electrons, so they have to settle for 2. So in general, atoms are most stable when they have a complete outer shell of 8 valence electrons. So if they had 8 on the outermost inner shell and 1 extra electron moving around there, they're perfectly happy to give that up. So then they got 8, and that's complete outer shell. Here I am. I'm going to read the man with the atom brain again. So here's my almost outermost shell, and it's got 8 valence electrons in it. 8 electrons, not yet valence electrons. And there's 1 more electron moving around here and on the outside. I'm not really holding it that strong. I'm very happy to let it go and somebody else take it. Now, I've got my 8 valence electrons. Now I'm happy. Why do they like 8 valence? Still waiting for somebody to tell me. That's a your idea. If they like 8. So the electrons most involved in the reactions are the valence electrons. And the elements in group 1, the first column, they have 1 valence electron. Group 2 has 2 valence electrons. Group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those have varying numbers of valence electrons because they not only have that outer shell, but they have another one that floats to it right under, and sometimes they act like valence electrons. So it's a lot harder to predict the third. But group 1 has 1, group 2 has 2, group 13 has 3, group 14 has 4, group 15 has 5, 16 has 6, 17 has 7, 18 has 8. So since 18 has 8, that's the noble gases. They say, I'm going to react. I'm happy the way I am. Get away from you, commoner. I'm noble. Well, you know, the noble gases, they're snooty, they're noble. So those in group 17, they said, man, if I had 1 more electron, I'd be happy. And they're going to try to push electrons away. Fluorine is up at the top on the right-hand side, group 17. Fluorine is the most reactive element that there is. It's going to take electrons from anything that comes in contact with it. So if you swallow too much fluorine, it's going to kill you. There was an episode of ER a few years ago, emergency room, where this guy's brought into the emergency room. He's a lab technician, and they bring him in because he's killed something on himself. He said, "What's he killed?" He said, "Hydrofluoric acid." How much? It's about a liter. I said, "Who's the next of kin?" I said, "What do you mean? I feel fine." So if you get hydrofluoric acid on you, it doesn't really burn your skin badly, but it gets inside your body, it forms through the bloodstream, and those fluorine ions, the fluoride ions, they are going to react with anything from the left side of the periodic table, and calcium's on the left side. They really can't attack your bone, but you know where else in your body calcium is very important besides your bone? Muscle. In order for muscle to contract, they rely upon calcium. So the fluorine is going through your bloodstream, and it says, I'm going to take some calcium away from this muscle, this part over here. And heart stop. For the zealous guy, you're going to be dead by tomorrow. Once it's in your bloodstream, you can't get it out. So if somebody ever gets into a chemistry lab class, high school, you will never, ever, ever fool with hydrofluoric acid. If you're in college working with it, you never sit down. And you always wear a lab coat, because if it fills on you, you quickly take the lab coat off, and you don't have the possibility of the stuff filling in your lap. You stand up. It's a very dangerous stuff because fluorine is such a reactive element. Of course, the second most reactive element, as far as taking away electron, is anybody have an idea what? Oxygen. That's why oxygen causes rust. So if it were not, we're going to get to this next week. If it were not for the presence of our DNA, we would be in trouble with all the oxygen in the atmosphere. It's so reactive, it'll stop all of the other reactions except the DNA. Forces it to do the right thing. Okay, so metals tend to give up electrons, non-metals tend to take or share them, and the metalloids, they tend to share also. So if the atom can't accept the electron, it's not enough to take them, it's all right, let's share. So let's say I have 6 valence electrons and you have 6 valence electrons. You're going to hold on to 2 of mine, I'm going to hold on to 2 of yours. So between the 2 of us, we're sharing and we feel like we have 8 valence electrons. So that happens in compounds made out of things from the right end of the periodic table. Okay, well, I'm going through some basic chemistry concepts. We're getting a semester-long chemistry course in 1 or 2 evenings. When electrons are attracted between one atom and another atom, they're going to form chemical bonds. If the difference in electron negativity is greater than about 1.7 on the periodic table of the electron negativity, that's enough of a difference that one atom is just going to take away the electron. So if it's between about 0.4 to 1.7, one of them's going to try to take away the electron, but it can't quite get it all the way away. So it's going to pull it strongly toward itself. And this is going to be a polar chemical bond. So I guess the polar bear that's familiar with this sort of thing. So if there's less than about 0.4 difference in electronegativity on that electronegativity chart, then the electrons are shared equally. Okay, so if I have a large difference in electronegativity, I'm going to get crystal. Sodium chloride, I get crystal. But if I have a very small difference in electronegativity, like carbon monoxide, carbon, or something with nitrogen, then it's going to tend to form a molecule rather than crystal. So water, H2O, the electronegativity of hydrogen and oxygen are close enough that they don't form a crystal. Oxygen pulls the electron strongly so it can't take it all the way away from the hydrogen. So the hydrogen is still there. So this electron is pulled over to that side. So on this end, sticking out, there's a proton, positively charged. That's why water is able to attract so many things, because the electron went that way, so we've got a positive sticking out. And water is a good solvent because a lot of stuff will be attracted to that part of sticking out. Okay, and then everything has got a chemical formula. The formula of an element is a simple right symbol from the periodic table. And for a compound, then it's going to be at least 2 elements. You write the symbol of all of the elements that make it up, along with subscripts to indicate how many of each, like hydrogen and oxygen, it's H2O, so there's 2 hydrogens and 1 oxygen. Carbon dioxide, you have 1 carbon and 2 oxygen. You have that as a 2 to be down there. So that's it. And then I'm hitting you with a bunch of stuff all at once. I know, both an epsilon chemistry course and one easy. There are many compounds that include ions that are made up of more than one element. A lot of these things, oxygen reacts with other stuff, and it gets together and it forms a polyatomic ion, poly meaning many. So generally they're made out of nonmetals. You should have sulfate, SO4, which is a -2 ion, carbonate, CO4, -1 ion, nitrate, NO3, -1 ion, hydroxide. Hydroxide is really common. And then there's also the only positive polyatomic ion is ammonium. Everybody ever smelled ammonia? Yeah. It's doing chemical reactions inside, that's why it's so bitter and unpleasant. So A lot of things involve polyatomic ions, especially acid. If you throw something with sulfuric acid, the SO4, is deeply involved in all of the reactions. And then there's something called chemical equations. It's not an equation in that it has an equal sign in it, like in math, but they call it an equation anyway. It shows how substances, that is, elements and compounds, will react to form other substances. You don't get new atoms that didn't exist before, but you get either elements that were not there in their pure form or compounds that were not there in their compounded form. So it doesn't have an equal sign. On the left side, you're going to have the things that are reacting, and the things that are reacting are called reaction. The things that are produced are called product. So the arrow is where not equals, but yield. This plus this yield, that's what's that, so that's like that. And then besides the subscript, this indicates how many atoms of each element, H2O or each subscript. So you're also going to have to show the relative amount of each substance. You should consider this as the number of molecules of each, but actually it's the number of moles. Did you know there are moles in chemistry? Yep, there are moles in chemistry. Amadeo Avogadro is the guy that invented the concept of the mole. So I always like to think of avocado, guacamole. So their coefficient, you have 2 of these, or 3 of those, you have 5 of those, or something like that. And then the chemical equations are an attempt to show how things happen. So you can't have new things coming into existence or old things going out of existence. You have to have the same number of atoms on the left as you do on the right of each element. Here's some of the common reactions. I do hundreds. Here's some of the common ones. For instance, I could have hydrogen coming together, CO2 plus O2. Notice there is a coefficient. So I have 4 hydrogen atoms on the left, 4 hydrogen atoms on the right. And the coefficient applies to both the hydrogen and the oxygen. So I've got 2 oxygens here, 2 oxygens there. It's a very common type of reaction where 2 things come together, 2 or more things. So it's a substitute or combination reaction. It's sometimes called a composition reaction. So in the other way, suppose I want to break down calcium carbonate into calcium oxide and carbon dioxide. That's called a decomposition reaction. So a guy went to the cemetery where he had heard that Beethoven was buried, and when he walked all around, he found the grave. And it's a weird thing. There's music playing for down in the grave. So it's going backwards. It's starting with his 9th symphony, 8th symphony, 7th symphony, going backwards. And he goes over to the cemetery and says, "There's a weird thing going on over here. What's it shop? There's music coming from Beethoven says that it's going backwards." He says, "Oh yeah, so isn't it weird?" No, he's composing. Anyway, decomposition reaction is the opposite of the synthesis of common composition. And then you can sometimes have where one part of the compound will switch out and replace another part. Zinc plus copper sulfate, here's the zinc sulfate plus copper. That's a single replacement reaction. So we have a single element going in and a single element coming out. Then you can also have a double replacement. Calcium chloride plus sodium sulfate. The calcium and the sodium good, and that's what you get. You could also have a complete combustion reaction, which is where you have enough oxygen available. And this is the same thing to think about. Any combustion reaction always produces water. That's how you put a fire out. Well, a combustion reaction is going to involve something with that hydrogen in it and oxygen, and one of the byproducts is going to be water. Then if you run out of oxygen, like carbon monoxide poisoning, if you don't have enough, you can get an incomplete combustion reaction, where this reacts with oxygen, you run out of oxygen, and you get carbon monoxide, which is very deadly because the carbon monoxide still wants another electron, and it gets in your lungs and it says, "Hey, give me an electron." And it takes an electron from something and it breaks down other compounds and goes. Okay, so these are not the only types of chemical reactions. There's hundreds, but there are a lot of others involving acids and bases and neutralization and things like that. You also may have a symbol put above the arrow. That would indicate heat. You can have a little lightning bolt showing electricity. A catalyst is used to speed up a reaction. If you've never heard of a catalyst, that's how farming keeps track of that's how the catalyst is. Catalyst is used to speed up a reaction many times faster than it would happen on its own. And when you get to talking about biology later on, the most effective catalysts are called enzymes. They're little molecular materials. They speed up reactions billion times faster. And very often you're going to put the state of matter, solid, this or that. An up arrow indicates that in your reaction, all of a sudden, oh, look at that, a gas stream bubbling up. Or a down arrow indicates I put together these liquids or gases and say, oh, a solid fell out. It's called a precipitate. And if you ever see a double-headed arrow, then indicates the reaction can go both ways, depending on the circumstances. Like if it's hotter, it goes that way. If it's colder, it goes that way. Okay, so you ready for a test on this? Okay, one more thing before we get into the history about how all of this knowledge came about is the shapes of molecules. There are 8 valence electrons around an atom when it's happy. But sometimes the electron came from another atom that's just hanging over right nearby. So if something is just all by itself, like a noble gas, it's going to have more or less a round shape. So if there's something that attached between one atom and, let's say, 2 more atoms, here's a water molecule. The big one is oxygen, the 2 little ones are hydrogen. It's going to have a faint shape. Because the oxygen started out with 6 valence electrons, just 1 and 2 more. It took 1 from this hydrogen, 1 from this hydrogen, but the other 6 that are already there, they don't like being moved around. They don't want to be bullied. So electrons work in pairs. This is something called the separate theory, valence shell electron pair repulsion theory. So if you've got 8 valence electrons, they want to go in 4 different directions. You got a pair here, a pair there, a pair there, a pair there, and the maximum separation you can get is not up, down, left, right. The maximum separation is 3-dimensional. So I'm going to try to simulate an atom that has 8 valence electrons, 2, 4, 6, 8. They're going to try to separate as far as possible in 3 dimensions. With genes, they're going to point all over the place. Well, if I had an atom that had 7 valence electrons, it's got 1 more, okay, there's no choice. Between these 2 atoms, it's got to form a straight line. It's a linear molecule. But if they had 6 valence electrons, it's very likely to form a bent-shaped molecule, because there's a pair up the top on the left, pair at the top on the right. Single electron down here binds to something. Single electron on the other side binds to something. And it forms a bent shape. And you can get all sorts of different combinations depending on how many valence electrons there are in this atom, and in this atom, and in this atom. So there were some predictions about the shapes these things ought to be, and they've been confirmed. You can send a beam of X-rays through something, and it bounces off the crystal. It gives you a pretty good idea of the shape of the circle. It's called X-ray crystallography. So these shapes have been confirmed. If I have something that's in a straight line, then there's a 180 degree angle between the 2 parts on the outside. Or if I have something where there's a central atom and 3 atoms around it, that's in a form of triangle, or trigonal. But I also very frequently will have tetrahedral. We have 1 pair there, 1 pair there, 1 pair there, 1 pair there. They're pointing in different directions to try to get it. I can't fit like that. To try to get as far away as possible from each other. And the thing of it, see, carbon does this all the time. Carbon has 4 valence electrons, and things attached to it at every angle that you can imagine. So because of that, carbon compounds in particular have all sorts of weird shapes. Like snowflakes, supposedly. No two have the same shape. I don't know how you know that. You have to look at all of the snowflakes. But carbon compounds can form all sorts of different shapes, and sometimes one carbon compound is a mirror image of another carbon compound, and the shape is almost the same except a mirror image. They call it right-handed and left-handed, depending on how light is polarized. And so back in the 1960s, there was a drug company that manufactured a tranquilizer called thalidomide. Anybody ever hear about thalidomide? Okay, well, it was a good tranquilizer, let's show that. Okay? And it worked great. But they didn't realize that it could exist in two forms, and they didn't really carefully control whether it's a right-handed or left-handed. If a pregnant woman took one form of it, everything was fine. If she took the other form, her babies would be born without arms and legs. It caused massive damage to the baby's DNA. So nowadays, if they, if you're pregnant or maybe some pregnant, they go through all the stuff at the end of some of it. They learned that from thalidomide. Because it's just that little difference in shape, where one molecule is a mirror image of the other molecule, that can cause major health problems. Okay, so now where did all of this stuff come from? I gave you this as a present state of our understanding. I guess I should say of our knowledge, of our understanding. Where did it come from? Well, there are some people that think that anybody that believes in God is stupid. Most of the great chemists down 50 years have been sick. At least they believe in some sort of a God. There's been a lot of Muslims contributing as well. So some of them, like Boyle and Lavoisier and Faraday and Maxwell and Compton and Newton, Dalton, Gauss, J.J. Thomson, Volta, Pascal, Lord Kelvin, Heisenberg, Davy, Eddington. There's just a few, and they were all very, very, very devout Christians. They were pretty too. Okay, there was one ancient guy named Democritus. He proposed, he was hundreds of years BC. He proposed that if you cut a piece of something like gold in half, it's still gold. Cut it again, still gold. Cut it in half, it's still gold. He said, logically, if you keep going, you're gonna reach a point where if you cut it one time, it's not gold anymore. You can't cut it past that. So the Greek syllable for cut is tom. So it was an uncut thing, a non-cuttable, and atom. If anybody has ever had a CT scan or a CAT scan, CT stands for computerized tomography, or CAT, computer axial tomography. And what they're doing is virtually cutting through. Take a little cut. So the com indicates cut. Now here's a weird thing that happened some years ago that nothing to do with that, but has to do with cutting. If a doctor wants to know what inside of a person's body, let's say that a cadaver in medical children and dissects the body to see what's in it. If there is also a service a doctor can sign up for. Some years ago, there were 2 executed criminals that agreed to donate their bodies to someone. So somebody went to them and said, look, after you die, we would like to dissect your bodies and we'll give the remains a decent burial afterward. Would you allow us to do this? They said, what the heck, I'll be dead. So it was a man and a woman. And when they were executed, they hard closed the body and then fit them up and took pictures of the top of the head, camera going around, took 1,000 fingers, shaved off a little bit, took more pictures, shaved off a little bit, took more pictures, went all the way down, and got a complete view of the inside of both the male and female body, and the doctor synthesized to that survey. So I don't know what they call the process. So it's similar to computerized tomography, but they actually did do tomography.
So the first guy that came up with an idea that there was such a thing as atoms was Democritus. And unfortunately for him, he was shortly before Aristotle. So Aristotle came along. He said, no, Democritus's ideas said that there had to be empty space in between atoms. And no, Aristotle, say there couldn't be any such thing as empty space. So therefore, nobody believed poor Democritus. Well, then, along the way, you had the alchemists who came along. They weren't concerned very much with theoretical chemistry, but they were trying to figure out how to get gold out of stuff. Like there was one guy who got a whole bunch of soldiers to donate buckets of urine because he said it's gold colored and so it must have gold in it. Well, he later was able to extract phosphorus, pure phosphorus for the first time. Um, he couldn't duplicate his work, so he sort of died penniless. But there was a guy that came along, and after it was all purified and the urine was gone, he bought this stuff. And if you take phosphorus, you can write on it, and it'll glow in the dark. And so this other guy played like he was a magician, and he did all sorts of stuff to make money. Okay, then the guy that really started the modern chemical theory was John Dalton. It had been thousands of years since anybody paid attention to poor old Democritus, but Dalton said, oh, come on, that makes sense. There has to be some lowest whole number of ratio where we put together two of these and one of those. And this was confirmed by experimentation. With Democritus, it was just theory, but no, Dalton, he said, okay, let's try two of this and one of those, and okay, we have almost nothing left over. Three of these and one of those, we got a lot left over. One and one, we got a lot of the other left over. He said, come on, down at the lowest level, there must be a small particle that's combining, and he called it the atom. So he came up with some ideas about the atom, and part of it was right and part of it was wrong, but not that much wrong. He said all atoms of the same element will be identical. Later we found out, no, they can vary slightly in the mass. He also said that matter was made of indivisible atoms. You couldn't divide it into anything smaller. Well, later on, we discovered protons, neutrons, and electrons. But still, it wasn't that far off. So we didn't just throw it out entirely. Like the ancient Greeks believed everything was made out of, you remember this? Earth, air, fire, and water. Well, that's been thrown out. It was just so far wrong. Was Dalton right? Well, he was a lot less wrong. Are we all the way right? We don't know, but we're a lot less wrong. We try to get less and less and less wrong all the time. And then Avogadro figured out that any two gases in the same container are going to have the same number of atoms, so he worked out the relative atomic weight, which was a key concept later on in Mendeleev working out his periodic table. Mendeleev was a Russian. He was actually a science teacher who became a chemist. I think that happens a lot where the science teachers have to have a general view where the scientists may focus on one specific aspect of science. So Mendeleev is a guy that came up with a periodic table for the first time. There was another guy, a German guy, who was working on it, but he didn't make any predictions. Mendeleev said, okay, there's three missing places here. We're going to find elements that fit in there, and he was right. So he's given credit for the periodic table. Okay, so then various people tried, I don't know why, but when Volta invented the battery for the first time, various people tried hooking up a bunch of batteries to get a high voltage electric current, and they ran it through a gas at low pressure. Why? I don't know. Why did you climb that mountain? Because it was there. So as people would run an electric current through a gas at low pressure, they'd see a glow. And you could tell it was not pure energy because it was in a sealed up container, but if you put a magnet near the outside and turn the magnet, the beam moved also. Energy doesn't respond to magnetism, but particles do. So Thomson's a guy that got credit for discovering the electron, even though a whole bunch of people worked on it. And then later on, his student, Ernest Rutherford, wanted to prove that his professor was right, kind of like butter up the teacher. Well, Rutherford wound up proving that his professor was wrong. Rutherford was no slouch himself. He also won a Nobel Prize. He discovered the alpha and beta and gamma types of radiation. A little before him, Henri Becquerel, Marie Curie, they had discovered that radioactivity existed, but they didn't break it down into the types. But Rutherford did break it down into alpha, beta, and gamma radiation. So he used a source of a radium source to send alpha particles through a gold foil. And he was expecting that it would just kind of go right through. As it turned out, some of the particles bounced right back. And the way you could tell is around the gold foil, there was a screen coated with a phosphorescent material. When struck with an electric charge, it would glow. So you could see, yeah, most of the particles did go right through, but some of them deflected at severe angles, and some even bounced almost straight back. So that meant there had to be, instead of just a spread out type of positive charge, it had to be concentrated in a small area called the nucleus. Well, he didn't know where the electrons were when they were not flowing, but he said they're just somewhere around. Later on, others came along and said, okay, let's do a better idea than that. Oh, along the way, there was a guy named Henry Moseley. He was a British guy, and at the time, nobody had ever heard of an atomic number. That's the number of protons. Well, Moseley was a student of Ernest Rutherford. And so he realized that different elements have a different charge in their nucleus. So he called it the atomic number. Rutherford had discovered the proton. Well, Moseley went a little past that, and he came up with the idea that multiple protons are going to give you different atomic numbers. Of course, the problem there was World War I broke out, and he was killed in the Battle of Gallipoli. He was a brilliant chemist. He probably would have made a lot of progress, except that he died. Well, and then to try to explain where the electrons are when they're not flowing through your high voltage electric current through the gas, Niels Bohr, a Danish guy, he was a brilliant mathematician. He came up with the idea the electrons must be orbiting at specific distances from the nucleus, and each distance has a specific exact amount of energy. And so if the electron gets some sort of energy applied, like electricity, ultraviolet, X-rays, it jumps to a higher energy level. But when it drops back down, it's going to send out a little particle of energy called a photon, which shows up as a color. So he did some calculations with hydrogen, which has only one electron, and it was perfect. Worked wonderfully. This was the beginning of quantum mechanics, because if you've ever heard the term a quantum leap, quantum is Latin for how much. A quantum leap is from here to here with nothing in between. Like if you're climbing stairs and you got a step here and a step here and a step here, you don't stand in between. You stand on this step or that step or that step. Well, likewise, quantum mechanics says that the electrons has either this energy level or this or this or this, and nowhere in between. Well, it worked perfectly for hydrogen, but no other element. All of the elements emit colors when you send electricity through them, or ultraviolet or gamma radiation, some high energy source going through a gas. So hydrogen was nice and predictable, but all the others, helium, fluorine, chlorine, bromine, they gave a bunch of colors, much more than what you would have expected according to Bohr's model. So Bohr, not Bohr, but others expanded on his idea and said, okay, there must not just be the main energy level. He discovered 7 principal energy levels that were responsible for all the colors you got out of hydrogen. But other people said, there must also be sub-levels that are close to those. And so the electron doesn't exactly go into that place all the time. Maybe there's another step a little bit lower, step a little bit higher. And so this led to further developments in quantum mechanics, and it also led to the realization that electrons are particles and waves both. Is an electron a wave or a particle? Yes, it's a wave or a particle. When it comes out of an atom and it's flowing in an electric stream, it's a particle. When it's in an atom, it's a wave. So other people worked with this, and they came up with ideas about how the various colors would be produced according to what energy levels there are. And it's pretty complicated. If you ever study on electron configuration, it can be pretty confusing, but it does a very good job explaining. So then Erwin Schrödinger came along, and he worked out the mathematics for how would you describe all of this. In science, you want to get into mathematics. And Schrodinger derived his wave equation, and I have no idea how you go about getting that. It's way too advanced for me. A lot of PhD scientists would have a hard time seeing how he derived it, but he was a brilliant mathematician. And he showed that the behavior of real things, protons, neutrons, electrons, behavior of real things could only be described with imaginary numbers. So it's like the thing is here, disappears out of real space, reappears over here. Wait, how did it get there? It didn't go through real space, it went through imaginary space. So imaginary numbers are necessary to explain the behavior of all of these things. So an electron is actually not a particle when it's in an atom. It's like a throbbing wave. And there's a bunch of electrons in most atoms. So you have all of these throbbing waves overlapping with each other, doing all sorts of interesting things. So I want to show you guys, those of you that are watching this video, you should go to that link, youtube.com/ and all that, and look for the Atom Song. I'm going to play it for you right now. I hope it comes across on the audio, but it mentions about some of these guys that did all of the stuff. You won't see the video on here, so you got to go look that up. Start at about 30 seconds. Dalton, Thompson, Rutherford, and Bohr, Wittenberg, and many, many more. Use them.
Was a weird Dalton did experiments, said I think it's clear. Atoms are tiny indestructible spheres. Thomson worked with cathode rays, said I disagree. A plum pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thompson, Rutherford, Schrodinger, and Heisenberg, many used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Hoare saw spectral lines for hydrogen and said it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it. There's no way to know the orbit or a path where the electron's gonna go. Schrodinger used lots and lots of fancy mathematics, made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty. Dalton, Thompson, Rutherford, and Bohr, Schrodinger and Heisenberg, and many more use their brains to venture in the realm of inner space and found the world. The atom was a weird and wondrous place. Dalton, Thompson, and more use their brains to venture in the realm of inner space. Found the world of the atom was a weird and wondrous place.
I like that video. I think it does a pretty good job of summarizing some of the major contributors and contributions. It did leave out the neutron, though. That was a guy named James Chadwick. Chadwick was a very shy guy. He enrolled in Cambridge University. He wanted to be in mathematics, and they stuck him in physics, and he was too shy to complain. Well, it turns out he wound up getting a Nobel Prize, too. He's the one that discovered the neutron. other people had said there's got to be more to it than just the proton and the electron, but nobody could discover it. He did a very low-tech experiment involving paraffin wax. I don't know what the details were, but he discovered, oh yeah, there's this thing called the neutron. And other people immediately began to use that to split atoms. And Chadwick said that he realized from that point that atomic bombs were not only possible, but they were inevitable. So for the rest of his life, he said he had to take sleeping pills to get to sleep. Imagine that if you knew I personally have opened the door for atomic bombs. That'd be kind of a tough thing, right? Of course, it did end World War II, but wow. So the Manhattan Project started up in the Manhattan region around New York. Chadwick was one of the principal British scientists on the project, and there were a bunch of other ones. Einstein was not directly involved other than writing a letter to the president saying, hey, Hitler's working on this. You need to get busy. So here's where we were last time. Moving on. If there's one atom that splits, this is supposed to be a uranium atom, uranium-235. If one atom splits, it's going to turn into things like barium and krypton, not necessarily those two, but the total mass is going to add up to the same within a tiny, 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 tiny little bit. But that tiny little bit releases a lot of energy. Einstein had an equation, E equals mc squared. That is, the amount of energy you get out of something is the amount of mass you convert times the speed of light squared. So for one atom, it's not that much. But if you just take one little chunk, you've got quintillions of atoms in that one little chunk. And so if you get a chain reaction going, you can destroy Hiroshima and Nagasaki. And of course, we have bombs that are far more powerful than that. There were a bunch of scientists that were involved in this, and they succeeded. They built new towns from scratch at Oak Ridge, at Los Alamos, I think at Sandia, and the people there were working on one part of an atomic bomb, and they didn't know. They just know, I make screws for a living. What's a screw go to? I don't know. But eventually they were put together into the atomic bombs. And actually, the atomic bomb was the result of splitting a uranium atom. So when it's finished, you have a tiny bit less mass than when you started. That tiny bit was converted into energy. But after that, people figured, okay, let's see if we could go the other way. Instead of splitting an atom, let's fuse two atoms together. So this is called a hydrogen bomb because you take two hydrogens and you smush them together into helium, and you lose a little bit of mass, but it's a much higher percentage. And so a hydrogen bomb is far, far, far more powerful. To set off an atomic bomb, you need conventional explosives like TNT. To set off a hydrogen bomb, you have to get the temperature up to millions of degrees. So you have to have multiple atomic bombs to start the hydrogen bomb going. And if anybody ever heard of a TV program called SpongeBob SquarePants, you heard of that? Okay, when the creators of the show were writing it and trying to figure out all of the background behind it, they happened to hire a marine biologist to make sure that all of the characters, all the creatures were moving, kind of reasonably for sea creatures. And so this marine biologist asked them, where are you going to have this set? They said, we don't know. He said, why don't you put it at Bikini Bottoms? Because the first hydrogen bomb test was at the island of Bikini, and it was far more violent than the atomic bombs. And when it went off, it was so dramatic that, somebody said, I'm going to make a dramatic new style of bathing suit called the bikini. And there was so much radioactivity left over from setting off the atomic bombs that set off the hydrogen bomb that the U.S. Army just bulldozed all of the dirt into the ocean at Bikini Bottoms. And the ocean bottom is incredibly radioactive. And that's why the guy said, look, you got your excuse to have all these characters do weird stuff. They're mutants because they're living around all this radioactivity. So that's why SpongeBob is at Bikini Bottoms. See, you learned something from this class, didn't you? Okay, so the project to develop nuclear fission for military use began unofficially during the earlier parts of World War II before the U.S. got into it, but Britain was under constant attack from the Nazis, and so anyway, the U.S. got involved behind the scenes, and they decided when the U.S. entered the war, let's move it over to the U.S. because Germany can't reach the U.S. Where if we're doing it in England, they could fly over and drop bombs on us. So when J. Robert Oppenheimer, the guy that was in charge of the Manhattan Project, when he watched the first successful test of the bomb, who was codenamed Trinity, to make sure it would work, it went off about 20 miles away, and he and everybody else was watching from bunkers, and he saw that thing go off. It was far greater yield than they expected. And I mentioned last time that he quoted one of the Hindu writings that said, "I am become death, the destroyer of worlds," because he knew, I made sure it all worked. It's on me. Well, anyway, later on, we found some other uses for nuclear energy, some peaceful uses. Anytime you want to produce electricity on a large scale, the way we do it now, you can do photoelectricity with sunlight, um, but anyway, the most effective way to do it is by spinning giant magnets past giant coils of wire. And when you do this, you're going to produce electricity. So you have to spin the magnet somehow. You put it in a turbine, and a human being would be, like half as tall as one of those things. You have something going past the turbine and spinning it. It can be the water coming down a mountain from a river, reservoir, something like that. It can be tides coming in and out from the ocean. It can be burning coal, burning oil. But the cleanest form of energy we've got so far is nuclear energy. Now, there have been a grand total of, I think, 3 accidents, and they were bad, but still, it's by far the safest form of energy, unless you live right there. If you do, then you'd say it's not very safe. So that's one of the things. You use the most powerful energy source known to mankind to boil water. And that spins a turbine and produces electricity in large amounts. So, people right now are all excited about got to get an electric car because they have no pollution output. Well, wait a minute. When you charge them, where's that electricity coming from? If it's coming from a nuclear power plant, okay, no pollution output, but most power plants are not nuclear. So to charge the thing, you got to have something burn somewhere. So maybe it's not burning right at your car, but it's burning somewhere else, and it's still polluting the environment. Best thing is just walk or get roller skates. Another thing that these are used for, space probes can use something, it's a heat engine called a Stirling engine. And as long as you have magnets moving past wire, you can get electricity. So they use the heat from a radioactive material to cause an expansion. The heat's radiated out into space. It contracts, it expands, contracts. And you could theoretically get thousands of years worth of use out of a small radioactive sample on a space probe. And then it's used in medicine for obtaining diagnostic images. It's also used for cancer tumors. You bombard a cancer tumor, you send a beam of gamma radiation through the tumor, and it's going to kill everything on the way in there and on the way out. But the alternative is death. So, okay, we're willing to do that. And there's another variation of that is there's a very localized tumor that has not spread. You can take an alpha radiation source and inject it with a needle right into the tumor. And as the alpha particles come out, they'll kill the tumor from the inside out. But the problem with that is a lot of times before you detect the tumor, before you detect the cancer, it's already spread. So it's not always that useful. In food preservation, the thing that makes milk rot and all of that is the bacteria in it. So you take your food and you put it under intense radioactivity, and it's going to kill everything in it. So when you drink it, you're drinking little bacteria, but they're dead bacteria, and they don't hurt you. If they're live bacteria, they'll make you sick. And also insects, you're eating dead insects, but it's just extra protein. So those are some of the peaceful uses of nuclear energy. And of course, nuclear reactors are used on a lot of military vessels, so I don't know, is that a peaceful use or not? So far, we haven't learned how to control nuclear fusion. Nuclear fission, splitting the atoms, yeah, we've got that pretty well down pat. Okay, and this was a lot of stuff, so I'm going to go back over. At the end of the chapter, I have review questions, so here come the review questions. If I could find them. Here they are. Yeah, the ancient Greeks believed everything on earth was made of what, and what? Yeah, earth, air, fire, water, earth, wind, fire, and water. And of course, they had the musical group back in the 70s, Earth, Wind, and Fire. Oh, they were so good. And then I'll get to the answers in a minute. Suppose you see a bag of bread that says contains no chemicals. Should you trust the label? Nah. What does the second law of thermodynamics have to do with how the sun's energy came together in the first place? How can chemists tell something is an element? How can they tell it's a compound? How can they tell it's a mixture? Difference between an atom and most types of molecules. The way to find out the chemical properties. What does a chemical change cause? Most common state of matter in the universe. Most elements on the periodic table are what? I'm going through this super fast, but just look at the review questions at the end of the chapter. That's what I'm getting to. On the left side of the periodic table, there's a tendency elements have concerning holding electrons versus on the right side. The Bible hints at something about the strong nuclear force that holds everything together. The shell of electrons in an important in chemical. There's one particular shell. Two examples of common types of chemical reactions. Molecules have a three-dimensional shape because of something to do with electrons. Okay, the first reported person that proposed the idea of atoms. Why was this discarded for about 2,000 years? And who was the person that proposed the modern theory? Who is given the credit for developing the periodic table, even though other people worked on it at the same time? Could you turn the temperature down a few degrees, please? And what led Thomson to conclude there must be particles smaller than an atom? What model did he propose for where they were when they were not going? And what did Rutherford use to discover that an atom had a nucleus? What is there about the size of the atom and the wavelength of light that doesn't allow us to see atoms even with the most powerful microscopes? You got these all? You're going to be able to just spout them out? No, in just a minute we'll get to them. How did Bohr explain the colors? How can science determine what elements are in stars without even going there? How does Schrodinger's work fit with Hebrews 11:3? And how did I left out the word did. How did Chadwick's discovery of the neutron affect him personally? And some non-military uses of nuclear energy. Okay, first, the ancient Greeks thought everything was made of earth, air, fire, and water. If you see a bag that says contains no chemicals, then it's an empty bag because everything is chemicals. It's all stuff off of the periodic table. The second law of thermodynamics says that energy tends to spread out rather than flowing together. And of course, the first law says there's no known process that can bring energy into existence or make it go out of existence. The second law says it tries to spread out. So here's what the second law has to do with how the sun would have first come together. There's no known process that would force the energy to come together. Right now, the sun is gradually radiating all of its energy out into space, as are all of the stars. Well, what would have started the process in the first place? There is no known answer. It's an unknown answer. It can be an unknown natural process or an unknown supernatural process. You can't test it either way. How can chemists tell something is an element? They try to break it down into simpler parts. If you can't do it by anything short of a nuclear process, nuclear reaction, then it's an element. How can you tell it's a compound? You can break it down into simpler parts with chemical processes, for instance, the addition of acids or electricity or some other reactive type chemical. How can you tell something's a mixture? Well, a mixture is relatively easy to separate. You can use physical processes, sifting, boiling, magnets, things like that. The difference between an atom and most types of molecules is that most types of molecules are the smallest particles of a compound. There's 7 elements that only exist in a molecule of 2 atoms each, but the other 111 are individual atoms. So generally, a molecule is the smallest particle of a compound rather than an element. And how do we find out the chemical properties? Try to get it into a chemical reaction. If it reacts, that's a chemical property. If it doesn't react, that's also a chemical property. A chemical change is automatically going to cause a change in the formula of this stuff. So if I have water H2O and I do a chemical change, it's not going to be H2O anymore. The most common state of matter in the universe is a plasma, which the stars are made out of. And of course, we have to conclude this logically because we haven't been to any stars. You'd have to go at night, otherwise you'd burn up. Most of the elements on the periodic table are metals. Even though we don't think of them, a lot of them, yeah, those are metals. The tendency of electrons on the left side of the periodic table is much weaker to attract electrons. Those on the right side is much stronger to attract electrons. So the ones on the left tend to give up electrons to the ones on the right, which rip them away. The ones on the right are bullies. And the ones on the right are actually smaller atoms than the ones on the left. So the little ones are the bullies. I always used to get one of the smallest girls in my class to come be the bully and take away the electron from the big guy like Anthony. You know, he'd be holding an electron and I'd say, you act like one of those non-metals. She'd go get it away from him. The little ones are the bullies. Okay, the strong nuclear force. Why don't all of those protons in the nuclei fly apart? We don't know, so let's give it a name. Let's call it the strong nuclear force. Every atom in the universe that has 2 or more protons ought to fly apart, but they don't. So, okay, sure, that's the strong nuclear force. This is what the Bible said. I like the English Standard Version. King James says consist, but English Standard said hold together. The strong nuclear force is not a purely physical phenomenon. Colossians 1:17 says of Jesus, he is before all things, and in him all things hold together. So this man who walked around Galilee for about 3.5 years, well, for 33 years or so, he was God. How hard would that be? This guy you've been hanging out with for 3 years to realize, oh, he made the universe. That's a mind-blowing idea. Okay, so the shell of electrons in an atom that's most important is called the valence electrons. That's the outermost electrons. The inner electrons don't generally do that much, but the outer ones, you're trying to get 8 electrons around the outside of the atom. If you've got 1, but there's another shell closer in that has 8, the atom is very happy to let the 1 go. So it says, I got my 8 now. And if an atom has got 6 electrons around the outside, like oxygen, it says, I want 2 more electrons. Give them to me. And it's going to take them. The most reactive element there is fluorine. The second most is oxygen. There's a bunch of common types of chemical reactions. There's hundreds, but when 2 things come together into one thing, like hydrogen and oxygen into water, that's a synthesis. Or if you break apart water into hydrogen and oxygen, that's decomposition. You can have single replacement, double replacement. Things can burn completely where you get carbon dioxide, or you can have incomplete combustion where you get carbon monoxide. Carbon dioxide is also bad for you because you need oxygen, but carbon monoxide actually actively attacks your blood to take another oxygen out. And one of the places that your blood goes through that has a densest concentration of cells is your brain. So carbon monoxide gets in your brain and it starts yanking away the oxygen atoms out of the brain and killing the cells. Okay, the thing that causes molecules to have a 3-dimensional shape rather than being flat, atoms try to have 8 valence electrons around them. Well, the electrons for some reason work in pairs. I don't know why they don't work in apples, but they work in pairs. That was a joke. So there's a theory that explains how this works called valence shell electron pair repulsion theory, VSEPR theory. And it says, okay, they work in pairs. And the pairs try to get as far away from each other as they possibly can. So I can't illustrate too well, but I'm going to put 1 foot forward, 1 foot back. one arm up left, one arm up right. So my limbs are as far apart as they can be. That's what the electrons try to do in the atom, go in 4 different directions. So something hooks here, hooks there, hooks there, hooks there, and you get a 3-dimensional shape. The first reported person to propose atoms was Democritus. I always used to give my students a test question, and I'd give them a choice: Democritus, Republicanus, Independentus. Most of them got it right. It was discarded for about 2,000 years because Aristotle, the big guy, he said, nah, there couldn't be any, I left in spelling, there couldn't be any empty space between atoms, so therefore there couldn't be atoms. The first person that proposed the modern theory, Dalton, Thomson, Rutherford, and Bohr. Okay, John Dalton, approximately 1800. He was actually a chemistry teacher rather than a chemist. And the person given most credit for developing the periodic table was a Russian guy, Dmitry Mendeleev. Thomson was working in England, and he noticed, not just him, but people noticed that if you ran a high voltage current through a gas at low pressure, there was going to be a stream of particles that became visible, and all of the gases gave the same result. So it wasn't just that hydrogen had this thing, but no, helium did, chlorine did, fluorine did, bromine did. Every gas you could put in there gave exactly the same results, even the ones that don't get into chemical reactions, like neon and so forth. That's why neon lights glow particular colors, because of the electron arrangement in neon. So Thomson said, okay, when the electrons are not flowing through, where are they? They must just be stuck around the outside of the atom. So the atom is like a blob of positive charge. And in England, they have a dessert they call a plum pudding. It's a raisin pudding. So he said, that's got to be what it's like. They're just kind of sitting there. Well, Rutherford came along and said, okay, I want to prove that my professor is right. No, I proved he was wrong. Rutherford and his colleagues shot alpha particles from radium through gold foil. And gold was chosen because you can beat it extremely thin, just a few atoms thick. It's one of the most malleable of the metals. And they found out that, oh yeah, look at that. Most of the particles did go straight through, but some of them bounced straight back. And the only way to explain that was that the positive charge must be concentrated in a very small area, the nucleus. So the reason we can't actually see this is because the size of the atom is thousands of times smaller than the size of the wavelength of light. So light is a wave like this, okay? The atom's like a grain of sand as compared to that. You can't see any details of it because it's just way too small as compared to light. So how did Bohr explain the colors? He said that the electrons must be orbiting the nucleus at specific distances that matched with specific energy levels. The electron could only move in distinct jumps, quantum jumps, and each one of those would release or absorb energy that corresponded to a specific color. So why is the grass green? Because the grass takes in all the colors of light, and the only one it doesn't use is a green. Get that trash out of here. I don't want that. That's the only color that the grass doesn't use, is green. So how can scientists determine what elements are present in the stars? By analyzing the spectrum of light. In the laboratory, we've been doing this for, I don't know, at least 150 years or so. I don't remember the guy's name that first did it, but it's very, very well known. Okay, if it's that pattern of colors, it's hydrogen. That pattern is helium. So we point a telescope at a star and we split the light out through a prism. Oh, that's hydrogen, that's helium, that's lithium, and so forth. So it's not just guesswork. It's comparing to 150 years worth of laboratory observations. And then, anybody remember what Hebrews 11:3 says? Schrodinger, from what I understand, was not a Christian. He was kind of a nasty guy. But his work, Hebrews 11:3 says, by faith we understand that the things which do appear were made of things which do not appear. Okay, Schrodinger showed mathematically that the things which do appear, matter, are made of things that do not appear, waves. I think that is so cool that the Bible predated quantum mechanics by 2,000 years. People say, "Ah, that's just an old fairy tale book." No, it's never had to be revised. Chadwick's discovery of the neutron affected him personally. He couldn't sleep without sleeping pills for the rest of his life. And some of the non-military uses of nuclear energy would be electric power generation, medical imaging, cancer treatment, food preservation, things like that. Okay?